Hello and welcome to my part of the presentation. My name is Alexander Hartelt. I'm currently working as Chair for Artificial Intelligence and Applied Computer Science at the University of Würzburg. And today I'm pleased to present to you OMMR4all Revisited, a semi-automatic online editor for medieval music notations. So the goal of our tool is the following. We have scales from different sources of medieval monophonic chants. One example, which is written in square notation, you can see on the left side. And the output of our tool are transcriptions, which can be exported to different formats. One example, which you can see on the right side, is the multi format. And the aim of our tool is to speed up the transcription process. So in best case, it would deliver the transcription automatically by itself. And our tool has already some kind of history with WoRMS, as it was already presented as a WoRMS 2019. And on this talk today, I want to outline some of the improvements and achievements we have accomplished so far with this tool. So first of all, I want to showcase the graphical user interface of our tool. So compared to the 2019 version, we did a lot of changes. A lot of changes were done in the back end, but we also did some changes in the front end. We added new smart tools, which are located here on the top side, which help in correcting the transcription. We have added new views, helping in locating errors, and we also refactored the presentation view. One change we did in the presentation, you can see on this slide, is we changed the symbol presentation. So now we have two colors, yellow and green. Yellow means the symbol is lying on the staff line. Green means the symbol is lying between two staff lines. And this was a small change, but it helped a lot in localizing errors. Also, what we have done is, what is new, we have integrated a completely automatic staff line pipeline. And this consists of several steps. We have a step for detecting the staff lines, which are on the right side displayed as blue polylines. We have a step for detecting the layout, which detects the music regions here located as or marked as green regions. We detect the lyric regions here marked as red regions, but we also detect the drop capitals marked as purple regions, and also detect the beginning of a chant and the end of a chant, even if they span over multiple pages. Also, we have refactored our symbol detection pipeline and also our lyric detection pipeline. And a step which is often forgotten in the literature, we have also integrated into our pipeline a step for aligning the syllables of the lyric to symbol sequences. And all of those steps are integrated into our editor, where you can see the results of the steps. You can use the editor to validate the transcription, and you can use the smart tools, which I mentioned earlier, to correct any errors in it. So as I mentioned, we have a pipeline, which is completely automatically. And on this slide, I want to showcase the results of it. And what you can see here on the right side is the results of our new approach or our new pipeline, and compared to our old pipeline. And I don't want to go too much into the individual figures itself, because they highly depend on the data that it was evaluated on the metrics, and so on. But what you can see is that we have improved across all steps in comparison to our old approach. And this is accomplished through better architectures, like, for example, in the line detection step, and in the symbol detection step, we are using now an efficient V3 encoder for our unit. And also, we are using post-processing algorithms to correct common errors. So, for example, for the symbol recognition step, we are using or we implemented rules to correct common errors, like missing clefs in the beginning of a staff line, or symbols which are in wrong regions, or we are also detecting or using competences of the symbols to correct missing symbols. Another thing, what is new, which I mentioned earlier, is we have step for detecting chant instances. For that, we are using mask RCN or YOLO. With those models, we detect the initials, and we use the initials and the reading order of the lyrics to instantiate or segmentate different chants. Another step, what is new, what we did is that we have improved our text transcription. So compared to our old version, which you can see here, we had problems with our text transcription, which was quite bad on unseen data. And this was caused because the data is quite difficult. As you can see on the bottom, the letters are quite similar, the syllables are spaced. Also, it's quite common that there are abbreviations. And because of that, we try to improve this step by having a chant database. So we created a chant database consisting of 46,000 different chants by collecting it from different sources. And we use this chant database to correct our raw transcription of our text models by automatically aligning it and correcting the errors. And this improved the text transcription by a large margin. And another thing, what is new is we have a syllable assignment step now included in OMMR4all, which uses a position and class matching, simple class matching, to align the syllables to the symbol sequences. So, and as I mentioned earlier, the main goal of our tool is to improve or to speed up the transcription time. And for this, we did some qualitative evaluation. So we compared the transcription time of two editors. One of the editors was already also presented at the WoRMS, I think at the WoRMS 2019, called MonoD. And the other one was our OMMR4all editor. And we measured or we compared the transcription time by measuring the transcription of 20 pages. And compared to MonoD, we had a speed up of 6 to 9. And compared to our old approach, we only had a speed up of 1.2 to 1.3. And yes, now let's conclude it. We, as I mentioned, this project has a practical view. We developed OMMR4all in the context of the Corpus Monicum project. So some of the features included in OMMR4all are tailored for the Corpus Monicum project. But we used OMMR4all for several transcriptions already. So we, for example, we transcribed the Geese book already using the automatic transcription of OMMR4all. We transcribed the Mulhouse source. Also, recently we retranscribed the Graduale Synopticum corpus, which is a data set or a corpus where the raw transcription got lost and only the rendered images were still available. And currently we have transcribed about 6,000 different chants using the automatic pipeline. And all of those transcribed chants are available under this link, where you can see the results of the automatic transcription. And currently we are working on applying the transcription to different notations, like, for example, the Rufnagel notation, and of course we are also trying to improve the pipeline itself. So.
Thank you very much. Oh, I already see the first question here. Antonio, please.
Hi. I wanted to ask if you could elaborate a little bit more on how do you perform the alignment between the recognized notes and the lyrics. As far as I'm concerned, you are doing object detection, so you are matching by closed boxes, or how do you perform this post-processing for making the alignment between the music and the lyrics?
You mean the alignment of the syllables to the symbols?
Yes.
Okay. Yeah. So we have the positional encodings of our text models. So we know where the syllables are located on the page, and also we for our symbol detection models we use a unit. So it's a segmentation approach. So with that we have also the position of the center points of the symbols, and we are only allowing syllables to, we are matching syllables only to symbols which curtain classes. So, for example, symbols which are looped can't be or don't have the possibility to have a symbol assigned to.
Okay, thank you.
Maybe one practical question for me, and then Yuji. If I had a similar data set, assuming I'm in library, could I make use of OMMR4all, and how would that work potentially?
Yeah, of course. That's we are looking for new data sets to apply OMMR4all on. So if you have a similar data set, which is in square notation, and then you can reach out to me, or you can also we can give you credentials for OMMR4all, which is hosted on the web, and so you can try it by yourself, or I can start the transcription process and give you the results of it, and then you can see it by yourself.
Great. Yuji.
I have a very technical question, and if you don't know, it's okay. You mentioned that you improved, among other things, the line detector. I'm curious as to what algorithms do you use for line detection, because I was sort of thinking about this. I know Philip mentioned this when he was talking about their project, that they also use a line detector. He mentioned that they use a Kalman filter. So
the line detection is also based on a segmentation approach. So we detect masks. So in the end, it's a binary mask where we can use a connected component analysis. And with that, you can we implemented an algorithm connecting the connected components to staff lines, and that's about it.
I was like wondering, maybe in general, because we have a standard like framework for doing object detection. We've got YOLO, we've got RCNN, and it's all about boxes. But I was wondering, is there such a system for lines that I would give two endpoints and it would just tell me this is a staff, this is a staff line, this is a stem, this is a beam? Could we train? And does there exist such a model? Like just curious, because it arose when I was programming the synthesizer, that some of the glyphs are like images, two-dimensional, and very many of them are like linear, just lines, and they are defined by the two endpoints. So I was like wondering whether there is such a model to which I would just give the class two endpoints and train it, and it would then give me this set of lines for a given input image. Like YOLO for lines, something like that. If you don't know, I'm just like, I'm gonna go and search.
What we deliver are polylines, so
okay, it's polyline.
I'm not sure.
Okay, thank you.